Okay, again, we talked about independent, dependent events. Very close. I'm going to show you just a tip and trick. All my classes seem to get it pretty fast. It's not much different than what we did yesterday. There is some intuition that you have to do, but it's not too hard to get. So what's the difference between one set or the other? So we'll go over it. Promise. Okay, copy that down. Now, in our dependent events, we're talking about two separate things. Okay, independence means that one event does not affect the other. In dependent events, we do see that. The whole journey we've been talking about is looking at sets and looking at unions, and we talked about mutually exclusive, and we talked about overlapping events, conditional probability, and the last part we're going to talk about is our independent dependent events. So this is actually the last thing we're going to learn. It's the last, sure, for this semester, for this year. It's the last thing we're going to learn for this year. It's not that long. Not until 2018. Okay. Now, when looking at this, we ask ourselves, how do we find the probability of dependent events? What changes for that if we don't replace a marble? If we eat a candy in a box, what's the probability of getting another type of candy? Okay, so we're going to look at this. What is dependent events? The way that we say it, and you guys pretty much know if it's not independent, it's dependent. The occurrence of one event affects the occurrence of another event. An explanation for this is using the deck of cards. And we say, picking a queen of hearts first. We pick it, it's a 1 out of 52 chance. There's only one of them in a deck of 52. We put it aside, like we're almost playing war or something like that, or we're playing Go Fish. What's the probability of picking up a jack of diamonds? Because there's only one jack of diamonds, it's 1 out of 51 because we set the other card aside. It changes the probability of getting it. Because we're not replacing it, we're changing up the sample size of this probability. The fact that you change the sample size changes the probability that you can get. And that's what we want to be able to see. Mm-hmm.
Like they legit make that work. And my brother takes it too seriously, and I'm like, you know what?
My wife wanted to do that, but I just felt too creeped out.
My parents told me if I ruined the Santa Claus stuff for Alan, that I'm going to be a big troublemaker and put me in a private school. So I was like, okay, with what money?
You never know. You never know.
I know.
Hope not. Ooh.
Yep. So scared.
I know. They're in a box. Should have found them. Sorry. It's probably in the back corner in the bottom of the bag. I haven't looked at in years. Oh, there.
I want a pen that says the Smiths.
Oh. Okay. This is our dependent events equation. So copy that down. This is not crazy. I'm going to show you an alternative way to look at this. We call this the multiplication rule. Again, we're talking about the intersection, the event that A happens. Given that we choose one of them and we don't replace it, what happens to if we can get B? Okay. Where B slash A is a conditional probability that a B is given that A has already occurred. Bless you. Bless you. Now, I'm going to give you this tomorrow, but I'm also going to give you the alternative way to look at this because I think conditional probability might be too tricky for some of you guys. Still not bad when it's just a conditional probability problem. But the fact that it changes when we have something that's already occurred might freak someone out. All right. Conditional probability, we're looking at the number in the intersection of the sets or the overlapping event A, event B over the probability of what it's asking us to find. Okay, and we'll look at your notes on that if you need to. For this probability, we're going to kind of change it up the same way as we did yesterday. Understanding that in independent events, we just take the probability of event A times the probability of event B. Okay, the sample size does not change for independent events. The way that we're going to write this out for the next one is the following. The probability of event A and event B for a dependent event will be the following. The way that you want to look at this is the number of the elements or the number of events or the number of trials or the number of outcomes that the first event can happen. The number amount in our first event. So, what's the probability of getting 5, or what's the probability of getting a blue marble without replacement and then getting a red marble? Blue marble would be our first event. Over the number in our sample size. This is the probability of just A. This is a probability of A. This is nothing new. This is how we find it. If there's 3 of 10 blue marbles, there's 3 over 10 chance of probability. The way that we're going to look at the second one is very, very similar. We're looking at the number of events inside the second event. Over the number in the sample minus 1. And this is conditional based on choosing not the same color. And we'll kind of get to that. This one? Yes. The other way of looking at it is if, let's say, it's asking us for what's the probability that you get a blue marble, you set it aside, and getting another blue marble. We're going to do slightly different, or let's say event A and event A. And we'll talk about both of these. This is not too hard, even though it looks like a lot. So copy down both of these. Because we're removing one of the samples, we're going to change it. So the second event minus 1. We're going to talk about them. One of them, it's better to just see problems. Trust me, it's not too bad. Okay. The top one is choosing a red one, not replacing it, choosing a blue one. The other one is choosing a blue one, setting it aside, and then trying to get a blue one again. And we'll talk about that. We'll see. It's better to see the intuition behind it. It's better to see a problem that involves this. To looking at the sets of just marbles and deck of cards and a spinner or something like that. The same thing like a Price is Right, getting $1 million, or getting bankrupt, or picking up the car that's on the table, or choosing a dark chocolate to Skittles, or find the probability of getting M&Ms for the next 3 times without replacement, or something like that. So here we go. You do not need to copy this down. I want you to copy down everything that I copied down, so you don't need to copy that up. Here's what we're going to do. We're just going to write a quick, brief explanation for this. It tells us a bag holds 4 white marbles and 2 blue marbles. So we have 4 white. So whatever I write down was what I want you guys to write down. And then we also have 2 blue. And it says you choose a marble without looking. So this is our event. First event is first choose. And then we set aside. And then second is choose again. So this is our experiment. We're just choosing 2 of them. Use the multiplication rule to find the specific probability and write it as a fraction. So we need several things. Can someone tell me my sample size for this? 6. We have a total of 6 different marbles in a bag. You can also think of them as like an M&M's bag, a small little bite-sized snack M&M's, right? They have like 6 of them, right? Assuming that there's only 2 colors, right? Now find the probability. So we're looking at our first one here. It says find the probability that you choose a white marble. So we're going to look at the probability of a white. And then we're going to look at a probability of a blue. A white, then blue. So we're going to look at white and then blue. Looking at our event, because we're choosing a white marble first, what is the probability of getting a white marble? 4 of the 6 chances. There's 4 of 6 total chances to get a white marble. Now, if I take that marble, how much am I taking out of my sample size? 1, so how much are we left with? We're left with 5 of them. So you always just want to take 1 away from it. If it says you take 2 colors, what's the probability of taking 2 of them, right? Well, in this case, we're just going to be basic with it. We're always going to take 1. Now, all we want to look at is now, because we took out 1 of our marbles, we're changing the probability of that. Now, what is the probability of just getting a blue marble? 2 of the 5 remaining. Done. All we want to do now is just multiply across. What's 4 times 2? 8 divided by what? You can reduce down if you want to, but I'm okay with just leaving it like that. That's it. That's all we're doing. So all it really changes from yesterday is because we're taking out 1 of them, we're reducing our sample size by 1. We're setting the divisor, setting it out by 1. Now the bottom one is slightly different too. What is it asking us to do? It says, find the probability that we choose a white marble, followed by choosing another white marble. And think about the intuition behind this. So let's look at this. Probability of choosing a white marble, and then choosing another white marble. So think about the first occurrence. What's the probability again of choosing a white marble? 4 of the 6. Now, because we took 1 marble away again, how much are we left with? Okay. But specifically, we've already taken out a white marble. 3 of the 5. If the occurrence is asking you to do it a repetitive time again, where you're using the same sample, the same event, we take 1 away from that as well. Because if we take 4 away, there's only a chance to actually get 3 of 5 left, assuming that we get another white marble, right? So that's all we're going to do. What's 12 times 4, or what's 4 times 3? 6 times 5? Those are the 2 cases. Done. Yeah? Is it making sense a little bit? Explain it like that? Okay. We'll see. We'll see today. We'll see today. Okay. Here we go. Again, what I want you guys to copy down is just copy down everything that's in this little red part. So copy down just 3 gold, 5 silver, and then we'll copy down 4 gray marbles. I messed this one up bad last time. It's because I was marking the wrong colors with the wrong marbles. So this case, it now has 3 different marbles. Again, we always have to look at the sample size. How many different marbles do we have in this bag? 3 different ones, but we have a total of 12 marbles. So a sample size of 12 different outcomes, right? I can choose 12 different ways to get a marble. What's most likely going to happen if we get a review? If you had to put money on it, how much money would you put on to get the first marble? What first marble would you first get? Silver, right? It has the most in the bag, right? Followed up by gray, followed up by gold. Okay, but that's not what we're worried about, but I just wanted you to see it. Okay, what is it asking us to do? It says, what is the probability that you pick a silver first? So we're picking a silver first. So picking a silver, and then we're going to pick a what? Gold. So again, it's telling us that we're not replacing it. So we're picking a silver, we're putting it in our back pocket. That means we're reducing it by 1. So let's see if we can do this. How many, what's our probability of getting a silver? 5 of the 12 of getting a silver marble. But we're going to take that marble and put it in our back pocket. How many do we have remaining? 11. Now we want to be able to see is how many do we looking at, how are we going to look at for our goal? 3 of the remaining 11 we have a possibility of getting. That's it. We're going to get 15 over 132. Good. That's all I want to see. Let's look at the next one. Let's see what it's kind of asking us. Here we go in our third set. 6 pink, 7 yellow, 8 clear, 11 black. Which one am I missing? Does it always require us to have 2 events? No, we can have multiple, it's just that we're not using those for those events. Now, what's our sample size for this one this time? 32. We have 32 different marbles in that bag. What's our picking first? What are we choosing first? Picking pink on the first draw, putting it in our back pockets because we're not replacing it. And then we're going to get a clear one. Getting pink and then getting a clear one. So, what's the probability of getting a pink marble? 6 of the 32 chances of getting it. Bravo. If we take 1 away from that sample set and we don't replace it, how many do we have remaining? 31. What color are we going to get on the second one? Which represents what? 8. Done. Multiply across. 6 times 8? 32 times 31? 992. You can leave it like that. You can reduce it. It'll probably reduce it for you. Do you know the other way of multiplying it like that? Have you ever seen what they do in, I think, Asia or China? Have you ever seen that? Where they multiply 2 numbers quick using sticks?
No.
Check this out. They do 3 sticks next to each other, and then they do 2 sticks down below. So this represents your 3 and 2. And then they go the other way to create this 31. So 1, 2, 3. So I'll try to be a little bit closer. And then they do the 2, or sorry, 1. This represents your 31. And all you do is you group them together. So the first set of terms we have, you count the intersections. 1, 2, 3, 4, 5, 6, 7, 8. That's 9. Then you're going to count these ones. When you're going to count the intersections of these 2, this is going to be 1, 2, 3, 4, 5, 6, 7, 8. This is 9. And then our last 2 here just is 1, 2. So it's going to be 9.
What?
992. It works. Blowing your minds. Have you ever seen that? It works for bigger numbers as well. I'm just saying.
I'm gonna try that. All right. Let's see that.
I'm just trying to help you out. This is another way of doing it. Okay. You can do it with any numbers and it'll work. Just want to be able to group them together. Okay, here we go. You're tripping. Too much, man. Too much. Do me a favor. These are the last two problems. Go ahead and copy these two down. Blow your mind a little bit. Was that pretty cool? Yeah. It works for it. Count the intersections and then group them. There's a lot of different ways. When discovering a lot of things in mathematics, people just have epiphanies. There's a thing that you can use to solve for Einstein's E equals mc squares using the difference between the mass formula for differential equations, or not differentials, but for integration. And there's something that just comes out of nowhere that you just need. And you're like, how did you think of this? You just did. Like, sometimes it's a lot of guess and check. You don't know how it works until you actually do it. So it's crazy stuff that happens. You're like, when does everyone think of that? But those are the breakthroughs that you see. So there's a lot of problems out there that they know the answer to, they know the problem, but they can't find the solution. It's kind of crazy. It's kind of like there is considered the largest number in the world. It's called the Googleplex. And there's a mathematical equation to solve it, but you can't show the work for it. From my understanding, you can't show the work for it. There's a way that you use mathematics to represent numbers. So you let them be variables and you let them be, sets. And so you devise this thing and you can come up with the ending number. I think the ending number is, I want to say 7, or I can't remember what it was, or 7. It's 1 through 9. I can't remember, but they know what it ends in. A Googleplex. But then you say, okay, well, +1 would be a bigger number, but technicalities. It's like I think it's 100 to the 100th power or something like that, or I can't remember. Look it up, Googleplex. That's where it's Gogle plex. It's not Google, not like Google. I can't remember. I can't what it was. It's exponentially large. There's some cool math behind it. You get some really cool math. That should have numbers.
Yeah, real quick. And it took him a year and a half to do an equation that it was the first person in college, he was the first person in history to ever solve it, and they had it up for years.
That's crazy. There's some cool cash prizes in mathematics to solve for these, and some of these breakthroughs that if you can find the equations and actually solve for the answers for these would open up new mathematics, and it's just incredible to see the different types that you can actually get from these, and it's just I'm nowhere am I near that. I have a degree in it. I have a degree in mathematics, but man, some of the stuff in my class I was just like, oh, it's hurting me. Stop, So I struggled in math a lot, but I think the more that you do it, the better you get at it. Just like practicing, you get better the more you do it. So here we go. Probability of a red card first. So probability of red, we're going to keep it, and then getting a black card. What is the probability of getting a red card? We're looking at all these cards down below. How many numbers? There's 13 of them, so we have 26 of them. 26 of how many cards? 52. Now, in the sense of this one, it's pretty easy. If we keep that card and we put it in the back pocket, how many cards do we have left? 51. Now, let's say we choose a red card and we put it away. Let's say we got a red card. What's the possibility of getting a black card? 26 left. So even amounts, even though it looks like they're different, they're even. This is a large number. What do we get? 676 over what? 2652. Seeing you thought this was hard. This is it. The next one, let's look at this next one. This one's going to kind of be another difference one, right? So look at, we're looking at proposing getting a face card, meaning a Jack, Queen, King, and then putting in our back pocket and then getting another Jack, Queen, King. Doesn't matter which type. Because we're choosing it twice, it does change up the way that we look at the probabilities. What's the probability of getting a face card? 12 of the 52 are face cards. This represents all of our 12 here. If we now have a face card and we put it away, let's say we get this first Jack here, Jack of clubs. How many clubs do I have remaining? 11 of the how many cards? That's it. 132 over what? Done. That's your homework. Okay. Now we're gonna stop here. How much more time do you got left? 10 minutes. Plenty of time to get started on your homework. Because it's Kindness Matters weeks. It's kind of me to give you homework. You're welcome. What the what? It's just I'll show you a different problem.
Like I can't do it.
I told Mr. Spiteri that you were his competition.
Mr. Spiteri, what did he say?
He said, "Oh, he's a pretty nice guy." And I was like, "Yeah."
Yes.
And it's basically said like a googolplex is so large that there's nothing in the universe that's that amount.
Yeah. It's so big that it's inconceivable. That's why it's hard to find the numbers in between it. They know the first and last number, but they don't know the numbers in between it, which is kind of incredible. So you guys need this little chart right here for your guys' homework. So let me.